Now we're thinking about electric current, moving electric charge. Previously, we've just been thinking about situations where charges stay put, more or less. But this is not entirely new. Thinking about current depends on some of the electrical ideas that we've already thought about quite a lot. So imagine this, a piece of wire, metal wire that can conduct electric current, and different points on the wire have different potentials. And if, as we've seen before, whenever there is a potential difference, there's an electric field between those 2 points that have different potentials. And the electric field always points in the direction from higher potential toward lower potential. So in this case, the electric field points left to right, and the direction of the electric field is the direction of the force on a positive charge. So if positive charges were able to move around inside this wire, they'd feel a force pushing them towards the right. However, what happens in a normal metallic conductor is that you have in each atom an electron or 2 or 3 that are bound only very loosely to their home atom. They can be pulled off their home atom quite easily, and once they're pulled off, then they're more or less free to move about. They can be pushed around by a force that comes from an electric field. And being negatively charged, the force that comes from the electric field and acts on a negative charge points opposite to the force that a positive charge would feel. So this is the force that acts on electrons. So what happens is that initially electrons are just sitting there on their home atom. You turn on the potential difference, which turns on the electric field, which starts pushing the electrons this way. So the electrons weren't moving when you first turned on the electric field, so they're getting pushed to the left. They'll start moving to the left. The flow of negatively charged electrons is to the left, opposite to the direction of the electric field. And this is consistent with what we've seen before, right? The force on a negatively charged particle will always push those negatively charged particles from lower to higher potential, the opposite of what the force on a positive charge does. Now, actually, when we're thinking about circuits, we imagine a situation slightly different from this, slightly different, but really amounts to the same thing, and just conceptually easier to think about. Instead of thinking about negative charges flowing one way, we pretend that the charged particles that are moving around and constituting the current are actually positively charged particles. And whenever we use I, that's our normal symbol for electric current, I always refers to this so-called conventional current. If you've got negative charges moving this way, that amounts to the same thing as positive charges moving the opposite way. So the conventional current, which is our imaginary flow of positive charge, opposite to the flow of electrons, is always going to be in the direction of electric field, because these imaginary positive charge carriers are being pushed in the direction of the electric field. So this conventional current made up of positive charges gets pushed from higher towards lower potential, always moves from higher towards lower potential, as I say here. Now, the one thing to, well, I'll get to that in a minute. Now add one more complication, because let's think about these electrons getting pushed to the left and picking up leftward velocity. They don't simply move straight to the left. There are lots of things in the way. There are lots of obstacles in the way of those electrons, like the atoms and the ions from which those electrons originally came. So all of those things can apply forces to the electrons and change the direction of their velocity and change their speed, so that the actual path of an electron is not just a straight shot in the direction of the force on negative charges, but it's a really could be a very, very complicated path. But overall, if you try to find an average velocity over some length of time, and then look at another average velocity over the same length of time later on, you'll get the same number all the time. On average, the velocity of those electrons is constant and pointing right in the direction of the force on a negative charge. We call that constant average velocity a drift velocity, and then we call the magnitude of drift velocity drift speed. Okay, let's imagine how that drift velocity gets started. So originally you've got electrons that are not moving. Then you turn on the electric field. Turn on an electric field like this. That'll mean that the force from the electric field acting on negatively charged particles like electrons is pointing that way. So initially you've got force from the electric field pointing that way, and this is at a moment when the speed of the electrons is just zero. They're all starting from rest, because when you first turn on the potential difference, which turns on the electric field, those electrons are all sitting on their home atoms. So at the moment you turn this on, at that moment there are no other forces on the electrons, so this amounts to the net force. So call that just time zero when you first turn on the stopwatch and start watching the electrons. Now, what happens to electrons as they flow through the wire is very much what happens to masses when they flow through any fluid, like a gas or a liquid. They feel a drag force. The net result of all of these atoms and ions that are in the way of the electron flow is to produce a net force opposite to the velocity of those moving particles. And just like the drag forces that you saw in 2201, just like those drag forces acting on something moving through water or moving through the air, the strength of that drag force increases as the speed increases. So of course, right at the start, when there is no speed, there is no drag force. But as soon as a little bit of acceleration has happened and this electron starts to pick up velocity in this direction, now there's drag force. And the drag force keeps getting stronger as long as the electron is speeding up. Higher speed means a stronger drag force. So after a little while, say time 1 a little later than time 0, this force from the electric field has not changed. It's still just as big as it was before, but now, since the electrons have picked up a little bit of speed, they now have a little bit of drag force pushing backwards. drag force in that direction, which means this drag force has canceled out a little bit of the forward force that was produced by the electric field. So now the net force is a little smaller than it was before. There's still a net force in the direction of the velocity. So anytime net force and velocity point the same way, you're speeding up. So the electrons are still speeding up, but they're not getting pushed as hard. The net force is weaker, so the acceleration it causes is smaller. So the acceleration is, or so the electrons are still speeding up, but now with a smaller acceleration. They're speeding up at a slower rate. But as long as they're speeding up, since drag force gets stronger as speed increases, as long as they're speeding up, this keeps on increasing. And this force that comes from the electric field keeps on staying constant. So what happens after a little while after that, force from the electric field is the same. Drag force has gotten larger because the electrons have been speeding up. So the net force now has an even smaller magnitude. So the acceleration is still there, but it's smaller as well. There's still acceleration in this direction. Acceleration always points to the same direction as the net force, but since there's less net force, there's less acceleration. But again, as long as there's acceleration, the electrons will speed up, and as long as they speed up, drag force increases. So this is at some time later than time 1. And then, after a while, the electrons have increased their speed enough so that the drag force has increased enough that it's now just as big as the forward pushing force from the electric field. And now you have equal size forces pushing in opposite directions, so the net force is now 0. So no more acceleration. So no more change in the electron speed. From this point on, there's 0 acceleration, and because there's 0 acceleration, a constant speed for the electrons is what you get from then on. But of course, remember, it's only a constant speed on average if you look at what's happening over some time interval. And that constant velocity that you get once there's no more acceleration is that constant velocity is the drift velocity. This is exactly the same as the same thing that we saw in the case of a drag force acting on something moving through the air or moving through water. As the object speeds up, drag force gets larger until the drag force is just as large as whatever force was keeping it moving forward. So at that point, with the forward force and the backward force equal to each other, there's no net force, so there's no more acceleration, so the object stops speeding up, and the speed that the object has achieved at this moment when it stops speeding up, we call the terminal velocity. The drift velocity is really the terminal velocity for electrons as they move through the metal conducting material, as they move through the wire. This is a kind of terminal velocity. In other words, if you were to make a graph of, say, electron velocity versus time, you'd get something like this. So the electrons start out at rest, 0 velocity, and as time goes by, they speed up. But as time goes by and they speed up, the backward force, the drag force, gets bigger, so that cancels out more and more of the forward pushing force. So that makes the net force smaller, so that makes the acceleration smaller, meaning as time goes by with smaller and smaller acceleration, the electrons are speeding up at a slower and slower rate. That is less and less additional velocity per second, until essentially the electrons aren't speeding up at all any longer, and you've achieved pretty much a constant velocity, and that's the drift velocity. All right, let's see. Okay, now, what else have we got here? But, let's think about this. Charged particles moving through some kind of conducting material, like we'll just think about a wire, and let's think about 2 points here. You measure the current at those 2 points, called current 1 and current 2. What is current? It's just the rate at which charge passes by any point. The number of coulombs of charge passing by this point per second. And the interesting thing is that no matter what this path is like, the current at any one point, the number of coulombs per second passing by, is the same as the current anywhere else. Same number of coulombs passing by, even if the wire in these 2 places is made of very different materials, even if they've got very different thicknesses, coulombs per second is the same everywhere along that path. And why is that? Well, we can understand why that happens if we think a little bit about what would happen if this uniform current were not true. What if, for example, current 1 was greater than current 2? So here are those 2 points in the wire, and we're imagining a current passing this way. It's current that we indicate with I, so it's the conventional current, the imaginary flow of positive charges this way, which amounts to the same thing as the flow of negatively charged electrons the other way. But let's imagine that it's really positively charged particles moving left to right. Well, if the rate at which charge passes by this point is bigger and the rate at which charge passes by this point is lower, then charge is going to pile up in this region here. There'll be more charge coming into this region than there is leaving. Right? The rate at which charge enters this region, which is just I1, is faster than the rate at which charge leaves this region, which is I2. So charge builds up here. And of course, what that means is that any more positive charges that are moving this way see this big pile of positive charge. So the charges that are trying to move this way will feel a repulsive force pushing them backwards. That'll slow them down. And if the charges heading this way slow down, then you have less fewer coulombs per second passing by this point. In other words, I1 decreases. That charge piling up causes a backward force, which causes the new charge coming into that region to come in more slowly. But with a backward force, all this is going to slow down. And so the rate at which charge comes in here gets smaller and smaller until this keeps on getting smaller until at one point I1 is now equal to I2. And when I1 is equal to I2, what does that mean? It means that the charge coming into this region, the rate at which charge comes into this region is the same as the rate at which charge goes out of the region. There's no longer any piling up anymore. In other words, current is the same everywhere, because if it weren't, if you had a bigger current at one place and a smaller current at another place, that's a condition that is not stable and that's a condition that cannot last. It's if charge piles up here because this current is bigger than this current, then this pile of charge causes a backward force on these things, slows these charges down until everything is back to equilibrium, until this current here is exactly the same as this current. So everywhere in anywhere in any kind of circuit, well, no matter what kind of material the charge is passing through, no matter what kind of circuit element the charge is passing through, it is always the case current is the same everywhere in any particular path. We call that conservation of charge. Okay. Current at any one place is the same as current any other place, no matter which 2 points you pick. All right, now what have we said so far? You need a potential difference to get an electric field. And if there is electric field, there will be electric forces on charged objects, and that'll push them around. And we need this push moving the charged things forward, because they're feeling at the same time a backwards push from the drag force, right? If this force were not there and the electrons tried to start moving, they would feel only the backward force, and that would eventually slow them down to a stop. So this force is necessary in order to have current. Or, to put it another way, the bigger potential difference you have, the bigger current you will get. In fact, it turns out that the current passing through any piece of a circuit is directly proportional to the amount of potential difference. And specifically, well, of course, that means current is equal to some constant times the potential difference. And the way we write that constant is this way. Current is potential difference, and we write the constant as 1 over some number that we call resistance. This constant is 1 over R. Resistance signifies exactly what it sounds like. This is a way of quantifying exactly how hard it is to push current through any piece of a circuit. For any particular amount of potential difference, more resistance means less current. And a few of the factors that influence the size of resistance are following. Different materials will have different amounts of resistance to them. So one factor is what we call resistivity. Each particular kind of material has its own value of resistivity. Conductors will all have lower resistivities, and insulators where you don't get current all have much higher resistivities. We use this symbol, the lowercase Greek letter rho, to indicate resistivity. Another factor is the length. The longer this piece of the circuit is, the more opportunities it'll have to bump into the obstacles, to bump into the ions and atoms and get slowed down. So just having to go through a longer path where it faces obstacles means it will be harder to push current through there. And then on the other hand, 1 over area. What this tells you is that if you pick some particular kind of conducting material, copper let's say, and stick with it, then this number stays the same. Use the same length of wire, but thicker wire. This number gets bigger, the numerator is constant, that means resistance is less. A wider area through which current can pass makes it easier for current to pass through. So let's say if you have a piece of a circuit that looks like that, a small cross-sectional area, that is, take a slice of this wire perpendicular to the axis of the wire. It has some area, and then there's a wider area. Downstream, if those two pieces of wire have the same length, and if they're made of the same material, they'll have the same value of resistivity. So same length, same material, but different thickness, different cross-sectional areas, means this changes, and if this gets bigger, this gets smaller. So the bigger, the smaller cross-sectional area through which the current has to pass, it's more difficult to pass through if it's in a smaller area, so that's more resistance. We see this similar kind of thing with, say, the flow of fluids. Gallons per second passing by one point in the pipe, what we called flow rate a few weeks ago. Flow rate is the same everywhere, just as electric current is the same everywhere in the path, but if the area is bigger, then there's less resistance, and then less resistance will make it easier for current to pass through. You get more current. Okay, now let's combine these two rules here. These are both useful rules, but let's combine them. let's also use this rule that we've seen recently. Magnitude of field equals magnitude of a potential change divided by the distance between those, the points that have those different potential change. Like this many volts of potential change if you move from one point to another point that's L meters away. Okay, so if we write potential change according to that equation here, then we have current equals field times L over R, but now write R, the resistance, this way. There we have it. But those L's cancel out, and now we've got just three terms here. We make things a little easier on ourselves by inventing a new quantity called conductivity, which is just the inverse of resistivity. This number measures how difficult it is to get current to move through some material, and so naturally the inverse of that would measure how easy it is to move current through some kind of material. And here's field times area times 1 over resistivity. So that's just, instead of writing 1 over resistivity, we can write conductivity. Here's the lowercase Greek letter sigma. So when we do that, what we end up with is current is 1 over R, which is the same as conductivity times field strength times area, the thickness of the wire. And we often use another kind of, we define another kind of current that's sometimes a little more convenient because that way we don't have to worry about thickness, actually, called J. We sometimes call it a current density because it is current divided by area. So here's current, and of course if you divide this by area, then this term cancels out, and all we're left with is J equals conductivity times the strength of the field. So really, these 1, 2, 3, 4 rules are all you need. All you need to understand what's going on anytime electric current is flowing. And what does this tell us? Well, if there's a potential difference, that means you get an electric field this big. If there's electric field, you get this J current, and if there is J current, you've got the regular, that means there is some I current, the regular coulombs per second. And in fact, if you don't change the length or the area of this piece of wire, keep all those things constant, then this tells you that potential difference is proportional to field. And if you always use the same kind of material, so this is a constant, then electric field is proportional to J. And if you don't change the shape, this is a constant, so J is proportional to I. Well, long story short, then start here. Potential difference proportional to field, proportional to J, which is proportional to J, which is proportional to I, or in other words, potential difference is proportional to the coulombs per second kind of current, which is exactly what we said way back at the start. Let's look at one little example of this. Got two pieces of wire. They're both the same length. And the same cross-sectional area. The one difference is they're made out of different kinds of materials. One material is a better conductor than the other. And the way we would indicate that quantitatively is that the better conducting material has the higher conductivity. So here's material 1, material 2. So let's think about this. First, what about the current going through segment 1 compared to the current going through segment 2? They have to be the same. That's conservation of current, right? The rate at which charge passes by any point in the path of current is the same as the rate at which charge passes by any other point. Well, these are the same, and the cross-sectional areas are the same, so the J currents are also the same, because J current is just current over area, and A1 is equal to A2, and I1 is equal to I2. So I1 over A1 equals current 2 over area 2. The J currents are the same. Now, what about electric field strength in these two regions? That's going to be different. Notice this. The J current, which is the same in both segments, is conductivity, which is different in both segments. So that means electric field strength has to be different in both segments, right? To keep this constant, if this gets larger, this has to be smaller. So to get the same J current in both segments, the better conductor, the material with the higher value of conductivity, has the smaller electric field. So that means stronger electric field, in the segment that has less conductivity. And that makes sense. In order to get the same amount of current, if it's just inherently more difficult to move current through some piece of wire, in other words, less conductivity, you got to push harder, which means stronger electric field, which means stronger electric force. Then what about potential difference? Potential difference between here and here, as opposed to potential difference between here and here. How does the potential difference between the ends of segment 1 compare to the potential difference between the ends of segment 2? Well, they both have the same length, so field strength is just proportional to potential difference. So in the segment where you had stronger field, you have stronger field because there's a bigger potential difference. Here, where the field was stronger in segment 2, it was stronger because the potential difference was stronger, which of course makes sense because to get an electric field you need a potential difference. And last thing, compare the resistances. And we'd see that, not surprisingly, in the wire that has less conductivity, in the wire where it's made of material that is just intrinsically more difficult to push current through, segment 2, that's got bigger resistance. And there are several ways we could see that. Here's just one. It's the same current through both segment 1 and segment 2, but in order to get the same current through both segment 1 and segment 2, potential difference 2 had to be bigger than potential difference 1. So if this is bigger for 2 than 1, this also will be bigger for segment 2 than segment 1 in order to keep current itself the same, right? If this is bigger, this has to get bigger by the same factor in order to keep the quotient, in other words, in order to keep the current the same. If this is twice as big a potential difference in segment 2, then segment 2 must also have twice as much resistance in order to get the same amount of current in both segment 2 and segment 1. Okay, so now it's your turn to try some things.